we'll set this thing up real quick. And I'll just assume everybody got stuck in traffic. Your video is going to be way higher quality than the OWL one I hear. I've heard a lot of negative commentary on the OWL.
Oh, yeah?
I don't know. How do you think OWL videos are? I never watched one.
I can send you the video after class if you want.
Yeah, I can probably put a link somewhere. Make that work. They don't seem to care about captions anymore. I think COVID kind of undid the concern about we can't post uncaptioned content. It probably didn't change the federal law that we were doing that in response to, but nobody seems to care. Alright, that's running too.
Can I close that curtain over there?
Is it throwing off your video?
It's just a little bit of glare, but it's not bad.
Okay. Yeah, we can if you want. I'd like to try to light up that corner a little bit so everybody can see the board, but I do have these front ones on. I was going to see how that works this time. How much glare does it have on there?
Oh, it's not bad.
Alright.
Yeah, that's fine. No worries.
Alright. Well, we'll go ahead and get started. Well, welcome to cs-430. I hope you all had a good weekend. It's one of our last hot weekends, so you can either enjoy the lake or enjoy the air conditioning one last time or whatever. Actually, next week it's supposed to be kind of warm too. Alright, so today we'll talk a bit about protection of memory. Although this is throwing me off for a minute, I was like, what am I supposed to talk about? Well, I was supposed to say note about protection of memory. So it is about protection of memory, and so that's why my note didn't make any sense to me. I thought I was supposed to talk about that. Not that. Alright, let's go talk about that. Alright. Another variable. Oh, I think I have an empty, no, it's not here. So, I'm going to make a little program here. That'll be a C program. And we'll make a few variables in the C program. These would be A, B, and C. And I'll go ahead and give them values, 5, 10, 20. All right, and I'll print them all out.
We didn't have homework in this class, right? Just in 311.
There's the homework that was due on Friday in this class.
Oh,
the
okay,
scavenger
this
hunt.
one. Okay, yeah,
Yeah,
I
that was
did
this
that.
one.
I turned it in.
All right.
I was thinking it was 311 for some reason.
And in 311, I posted lab 2, so if you want to work on something in that class, there is something available. Although that's this afternoon's topic.
17th, I think.
What's that?
It's September 17th, I think, for the due date.
For the lab 3 or which?
Something. Maybe
Something.
it was a different course.
Project 1 in this class is due on the 15th.
Yeah.
Okay.
Alright, so let's do a little program here. Okay, so pretty straightforward, right? And it should print out like 5, 10, 20. Alright. Alright, 5, 10, 20. Cool. We passed the first day of CS211. Alright, so I could say here something like A equals 243, and that would change A, right? So then it should print out 243, and then 10, and then 20. Alright, but what if I want to change the thing that's at the address that A is stored at? So that's just a really convoluted way to say A, right? We're going to take the address of A, that's what that means, address of A, and we're going to change the thing that's at the address of A. Alright. So that's like if I want to bulldoze the thing that's at the address that my house is at, you see? Alright. So, that work? Alright. Slightly convoluted, but yeah, it works. Alright, what if I say I want to change the thing that's at the address that A is at plus 0? Again, we're being convoluted and saying the same thing, right? Alright. Cool. How about plus 1?
Yeah,
C.
it's gonna put it in a different spot in memory.
Yeah, and it
Yeah.
turns out that it just so happens it's putting it in the spot in memory that C occupies.
That's weird.
So it's kind of like if I say, let's go bulldoze the house that's at the address of my house plus one. All right. I mean, I didn't say C anywhere in this line, but we changed C. What if I say plus two? I wonder if B happens to be stored there.
Yeah.
Yeah, hey, it is. Oh, yeah. What's after that? Probably nothing good. It didn't, no apparent effect. I don't know what we
You gotta
overrode.
make a variable D.
Whatever we overrode, I guess it must not have been used again. Okay, that happens sometimes. Okay. All right. If we start doing this to a lot of locations in memory, eventually we'll cause some kind of crash like
Segfault,
that. Basically, yeah, we can change this by arithmetic. Okay. Well, the system is internally consistent. So if we say something like, let's change the thing that the address of C minus 1 points to say 357. All right. So we know that this line up here, the thing that's at the address of A plus 1, happened to be C. So if we take C's address and subtract 1, logically speaking, we should end up at A, right? Yeah.
Should you get the same relative memory addresses every time you run, or can it be like arbitrary? Like we have sometimes it'll be B, sometimes C, or...
Yeah, it's not necessarily going to be consistent there, and in fact, I think it just wasn't. Because you see we changed B instead of C. So if I change this to B,
Change C.
all right. So yeah, I mean it varies where they are. So we could print out the order. We could say something here like print out the address of A. Up here, I'll just grab this line and get rid of this line. Instead of this, we'll print the address of A, and that'll be we'll print it out in text. Same thing here. The L, by the way, means it's long, like it's a 64-bit. All right. The addresses here are just for our convenience right there. A, B, C. All right. Okay. Whoa, no way. I didn't hit any of them. You can see why. A is actually stored last. Then there's B, then there's C. All right. If I run it again, it'll be consistent there in the ordering when I run the same file. If I compile it again, it'll probably again be consistent.
Switch them all around now.
But if I make a trivial change in the program, I don't know what I want to change here. Just let's say we take address of B there. All right. Seems like a trivial change, right? Well, look at that. It seems to have changed where they ended up. It depends on how the compiler decides to lay everything out. I see. I changed it back to something consistent. So if I say B plus 1 and A minus 1, well, again, what will the compiler do? Hey, look at that. We actually did manage to get them to change each other. All right. What if I go ahead and build it differently? Let's say I build it with optimization level 3. That should come out a little bit different. Yeah. Now they're in a completely different order.
Yeah.
All right. Is it consistent if I just do it unoptimized that the little trick works? Yeah. Yeah, it is. All right. So, kind of takeaways here. You can totally use arithmetic like this to change a different variable that you didn't say anything about in your program. But I wouldn't really recommend it because the results aren't very consistent. It's not the way you're expected to program. So when the compiler authors write their compiler, they don't really think about this as a use case. And so when they're coming up with the algorithm that the compiler uses to lay variables out on the stack, there's no particular reason they need to be stored in any particular order. We have a bookshelf at my house, and it's randomly ordered. And so if you say, I want the book right next to the cat in a hat, what you get might actually vary from day to day. But you know, there's always one next to it. You could always say that, I want the book next to the cat in a hat, and it'd be fine. You just won't necessarily get a consistent result. All right, so I titled this thing Note About Protection, except that I forgot the E. So the thing I wanted to mention here about protection of memory is that in C, you don't actually have very much protection of memory. C will let you say about anything you want, whether it's a good idea or not. And the kernel will enforce the occasional restriction on you. So if we were to say after this something like, I actually wanted that, or what am I doing? All right, suppose I want to say change the thing that's at the address of main to 400. All right, it'll probably give me a data type violation straight off, but we can probably fix that. Yeah, let's say the thing that's at the address of main. All right, and we'll say that it's an int pointer, excuse me. So the address of main, we're going to say pointer to number, change the number that's there to 400. All right, that compiles. Yeah, it doesn't work. All right, and the reason for a segmentation fault here, see if Valgrind has any additional commentary. Nope. Oh, no, there we go. So process termination with default action of signal 11, signal for segmentation violation. Bad permissions for mapped region at address such and such, right there. And so basically we're not allowed to change the region of memory that we just tried to change. It's actually a security measure that we ran into here. Programs aren't allowed to modify their own code anymore. It used to be that they could, and so you could write a program that actually changes itself while it runs. That could be cool, but not a lot of applications are found for it, except that if you could figure out some way to make the program do that, it could be a security vulnerability.
Yeah.
And so security vulnerabilities are like the main application for this feature. So,
It installs turns itself into a virus later after you install it.
right. I'm reasonably certain you can compile Linux without that feature if you want to. Most of the stack and security features can be disabled if you want to, but not a lot of reason that you would.
That first error up there, the L value required as left operand of assignment.
Yeah, so I wasn't thinking that well when I typed it. You see I said the address of main. But main is a function, and so the address of main is related to where the function is stored in memory. And so it's not really something I can change. And so it's an invalid L value, like a left value, because it's not a mutable quantity or variable or anything like that. So you have to put something on the left side of the equal sign that can actually be changed. You get a similar error. Oh, I want to do this. Suppose instead of this whole thing here, I say something like 5 equals 400. I'll get an invalid L value with that one too. L value, yeah, it's actually the exact same error. All right.
Wait, so can you assign a new value to the address of a constant then? Like, could you assign a new value to the address of 5?
Something like this. Like A is now going to be actually B.
Like, say if you declared A as a constant, could you change the value at the address of A? Like,
Oh, sure, yeah. All right, let's check that. Error assignment of read-only value. But look, I think it actually caught us on the other one too. See? All right, what if I cast this to a regular int star? Now we can change it. So you can defeat const like that if you want to, but it does actually enforce it, at least for this construction here. Now the reason for that is that const int is, it's an attribute of the data type, const. And so if we've changed data types using a cast, if we said, when we said int star there, we're now using a mutable data type. And so now it becomes a valid L value. Yeah, so you might say, well, couldn't you do this easier if you just said something like int a equals 10? I don't know, maybe. Nope. Can't just cast it away like that. You have to be a little bit more sneaky. But that's sneaky enough. I suppose you could also do something like this. You could say like, alright, int star AP equals int star A, the rest of A. And now we can just say like the thing AP points to. Yeah,
Yes.
that's 43.
Yeah. But it wasn't a const anymore, so.
Oh, let's make sure that works then. Yeah.
Okay.
All right. Okay. All right. Remember that const here is again something that's designed to kind of protect you from yourself in a way. It's kind of like the the power supplies that we put in computers. Is the computer would have just a little bit better airflow if we pulled the case off of this power supply right here. And the power supply is robust enough mechanically that we'd be fine running it that way. I've actually run one that way before when I had the CPU heatsink really close to the power supply and I wanted a little bit better airflow around it. But this area of the computer actually handles high voltages, and so the case is there to keep you from accidentally sticking your finger in it when you try to remove a RAM module while the computer's still plugged in. So, do you want to defeat it? All right, maybe, I don't know. All right. We're not in security class, so I shouldn't talk about security too much. Just to mention that
It does
C
fun
doesn't,
stuff.
well, I mean, there's different categories there, right? It depends what you're trying to do. I mean, if you're expecting criminals to come, then you need good security. And if you're just like, I want light switch covers in my house so I don't stick my finger in them in the dark, well, it's okay if you can defeat it. All right. So let's talk a little bit about allocating memory. Now that we've talked about, oh, I should mention one last thing about protecting variables before we move on. Okay, so this kind of game here, this is going to be a lot of fun in security class. We're not going to really go further into it here. I'm just showing you that there's not a lot of points where the language is going to be like, no, you can't. But in security, we're going to have all kinds of fun doing this. It's going to be great. Already looking forward to it. Okay. So allocating memory, malloc and free and calloc and stuff. All right. So in the kernel, you have a kalloc, and it has the same parameters as the user space calloc. And so the model to allocate and deallocate things looks basically exactly the same as it does in user space C. Not C++. There's no new or delete or new array or delete array. Just the kmalloc and kfree and whatnot. All right, so one interesting thing about the computer is if you hit if you hit in like man kmalloc into Google, you actually get a manual page for kmalloc. I've had trouble getting these things installed correctly on Debian, but you can just use them here. All right, so kmalloc here takes a size and, oh, I'm sorry, I just said this wrong this morning. All right, it doesn't take the same parameters as calloc or malloc. It's a little bit different. All right, we have the size here first. This is the number of bytes that are required. That's the same parameter as malloc would have. If I pull up malloc's man page here, you can see that our first argument here is the size, and works the same way. It allocates size bytes. All right, the second one on kmalloc is this flags argument. All right, so there's a few different flags you might have on different types of memory you might want to allocate in the kernel. All right, we'll start writing kernel modules pretty soon, not today, and talk about these ones. But mostly you're going to end up wanting like GFP kernel, which is normal kernel RAM. And malloc may actually sleep, notice the may sleep here, This is going to be significant later. There's some times in the kernel when you really don't want the kernel to sleep. If you do, it'll cause some kind of problem. Anyway, that's kind of the standard one. All right, the atomic one is not going to sleep, and so you can use it inside interrupt handlers. We'll talk about interrupt handlers later. And there's a few other cases that are somewhat specific. There you go. All right. So, how these work in C and regular C. All right, these really are about the simplest kind of memory allocation you could have, which in some ways almost makes them more difficult to use. You know, if you're like, hey, look at that. This person has just built a table just like this, using nothing more than a factory full of tools. You know, not necessarily like, wow, what kind of person does it take to make a table using only a table factory? On the other hand, if somebody comes up and they're like, I built that entire table using nothing but my car keys. You know, now you're like, yeah, that's one really good table builder or somebody who's really full of it, you know? So just because it's a simple tool doesn't necessarily make it easier to use. All right, it's easier to understand what it is. Okay, I might have a malloc demo in here. Let's do this. I have scrambling. I've got a lot of ones. Segment addresses, old examples using argv, allocation.c. Let's take a look at that. All right. Oh, that's right. This is a long and complicated demo. Let's not go there today. It generates scrambles of words. Like you can scramble words in a bunch of different ways. I want a really simple one. Okay. Okay. We'll grab stdio, and I think malloc is an stdlib. All right. There's a lot of stuff I just plain don't remember on a day-to-day basis. Stuff like what header file is malloc in for sure. Maybe it's in unistd or something. I think stdlib with about 70% confidence. 70% for me is enough to write it there and look it up if it fails. All right.
It's stdlib.
Okay, cool. Okay. Our memory equals how much memory do we want today? How about a kilobyte? Nah, let's have a megabyte. No, let's have a gigabyte. All right. There's a gigabyte. Okay. All right. We got a lot of memory. What should we use it for? Like an array of integers. This can be at the beginning of it. All right. Now we've got an array of integers, and that's part of our memory that we've got here. So we can go ahead and use it. We can say, we'll make it a little bit bigger. Int I equals 0. I is less than, use the first 10. All right. So we'll say int set position I equals, maybe that's complicated. I was going to say the sum of the previous ones. Oh, sure, why not? This is some of the previous ones. All right. So if we're going to do the sum of the previous ones, we'll just go ahead and do a little if here. We'll say, we can accumulate easy enough. We have to put something in there. The sum of the previous ones is just always going to be 0. Because the first one will be 0 if there's nothing before it. And so, I just say if we're on the first one, it's a 1. Hey, that'll be a Fibonacci series. No, not quite. Fibonacci series is the sum of the last two. All right. If I equals 0, all right. J equals 0, J is less than I, J plus plus. We need an accumulator. Needs to start out at 0. So we'll say accumulator plus equals and set position J. Okay, so that should add up each of them. And that should add that to the accumulator. Does it work? Oh, I don't know. All right. print them out in a row. We'll use array notation, so it looks kind of cool. So I'll go ahead and print up an array bracket to start, and then we'll go ahead and print up %d comma space and set position I, and then we got to print the last one, or the closing brace. But there'll be one little complication here. We'll fix it in a minute. I'll show you why, and we'll see if this works at the same time. Oh, I forgot a new line. And it's not working. There's a new line. Why are we not working? So for the first one there, if I is 0, then ints at I should be 1. Oh, but then we go ahead and change it to a 0. Well, that would be a problem. You see that? Because we set it to 1, but then down here we make an accumulator of 0. J is less than I, so this loop actually doesn't even run. And we end up putting a 0 back into it. Oops. All right. Hey, there we go. All right, here's the formatting bug. Here's this extraneous comma in space. It's like, can't we just get rid of that? Like, hit backspace a couple of times? Sure. Backspace, backspace. There we go. Better. All right. We've got more space. I think we need a phrase. All right. I want to use some of our memory. But we'll go ahead and move on a ways. I mean, we've got our array of integers. We don't necessarily want to lose that. Maybe we like our array of integers. How much should we use? Well, 40 bytes, right? Size of the int times 10. So we'll just say plus 40. All right, now we're past the end. All right. I can go ahead and copy a phrase into here. There are neighborhood, but they fear my walnut tree. This is because I have crazy killer cats that patrol my yard. They eat squirrels. Squirrels know this and stay away. All true. Every word of it. All right. Now that we have that, I suppose we can just print it out or something. All right. I can show you that we still have this thing here if I just take our little printing thing and move it down after that. Whoa, we got an implicit string definition thingy because we didn't include SGO. I kind of wish GCC had an option to just like add it to your file. Like it knows what we need. Couldn't have it just like, you know, press Y if you think this is right and you want to add it. All right. Or they compile it GCC-A and it like goes through and auto fixes everything it told you about. Oh well.
Could write the code for that.
Yeah. All right. Yeah, I mean it works. Okay. So what we've done here, this is called slab allocation. All right, it's on my notes, so I'll put some note there to preserve that thought. All right, the reason it's called slab allocation, we've asked for a bunch of memory, which I should probably just name slab. There we go. This will work. I wonder what else I changed. I always wonder that with cut and paste, like, where did I find, you know, not cut and paste, it's, whatever it is, search and replace. All right, so, slab allocation, you basically ask for a bunch of memory, and, like we did, and then you go ahead and use the memory for whatever you like. And it's a reasonable model to follow in a lot of ways. So the request for memory is kind of generic. So you go to the hardware store and you buy a piece of plywood, you bring it home. Yeah, the hardware store doesn't know or care what you use it for, you know. You could be using it to build a table or a paintball fortification. You know, they're whatever. you could cut it in half and you could use half of it to build a table and half of it for a paintball fortification. No problem. Alright, so it's the same kind of thing when you ask Malik for memory. You get some memory. In this case, I got an excessive amount of memory. I got us a whole gigabyte. And we use different parts of it for different purposes, having only asked the operating system once for memory. Alright, so you can combine allocations that way and do that. And if the plywood buying example, say you did want to cut it in half right down the center and have a 4x4 sheet and another 4x4 sheet. I guess you could have gone down the center the other way too. But anyway, suppose you want to do that. And you're going to use half of it for one thing and half for another thing. Half of it is going to be a table for your goats to jump on in the yard, and the other half is going to fill a great big hole in your floor that happened when you got a new impact hammer late at night and wanted to try it out and weren't thinking about where you were. Two different purposes. So you could go to the store and try to buy 2 half-sized plywood panels. You probably spend more that way. Usually the 4x8 sheet is the deal on plywood. Plus, if you go to the store 2 separate times and buy 2 separate half sheets of plywood, you will spend a lot of time. Alright, this is the main advantage of the slab allocator. There's not a price here in terms of dollars for going back to the kernel and asking for memory again. So maybe I should state this more as it's like the free hardware store that you already own or something. But there's definitely an advantage in combining the trips here. Slab allocators tend to see a lot of use in stuff like video games, but there's also a slab allocation system inside the kernel. Alright, now you don't have to slab allocate stuff. Suppose down here you're like, alright, well, I want you guys should be free of this stuff too. Let me put this here while I'm thinking of it. Alright, so we'll be done with the slab allocation. Suppose you just wanted space on the heap for something else. Say you just wanted space for one double. Alright, you can say something like double star, I don't know what it is, number. Okay, it's actually the address of it. Pointer to the number. Alright, we'll cast it right here. Alright, so I just went ahead and said size of double. Size of double will return 8 on this platform. Doubles are 8 bytes on x86 64. But if I ever build this on a different computer that had a different definition of double, it would go ahead and update. Double doesn't vary really by platform. It's not like int, for example, which is guaranteed to be at least 16, but is usually 32. Alright, then if we want to use it, we can say something like pointer to the number. Maybe we say the thing it points to. Is equal to, I don't know, 4.321. Sure. Alright, cool. I don't know what we want to do with it. An LF is a double in C, a long float. The thing is that pointer to the number. Alright. There's a Vim autocomplete feature. I've been learning how to use one feature of Vim per year approximately, because it takes a while for it to become ingrained. And I think maybe this year will be the year of the autocomplete feature. There's one year I learned the feature where you can select blocks of stuff. Like if we're up here and we're like, I don't want to say include there anymore, then you just go like that, which is pretty cool. And then if you wanted to actually have include on these, I realize I'm making a mess of my program, you can put include right there. Yeah, not really useful in that example. But there's a lot of examples where it is useful. Alright, anyway, so that's kind of on the side. Alright, so this is not slab allocation. Okay, because we asked the kernel specifically for a spot of memory to do something in particular. It's like if you go to the store and you come back having bought, one screwdriver or whatever. It's like, that's what I wanted, that's what I got. Alright, there's plenty of times when this is the appropriate model too. For example, if you only needed memory to do one thing, and you weren't sure you were going to need any more memory for anything else, and so you asked for exactly what you needed, and that was efficient, because You got what you needed and nothing else. All right, so a couple different ways to go there. Okay, and I went ahead and freed them. I don't talk about calc so much, except to mention, usually the reason people use calc is because calc sets your memory area to 0 ahead of time. And so if you want to skip doing like malloc and then writing a loop, you can use calc. Calc also has slightly different parameters. You give it a number of memory items and a size of each item. And with malloc, if you're doing the same thing, you would just multiply those two together. And so either one works fine. With malloc, you just use a times instead of a comma. Anyway, that's what calc is. If you actually look at these backwards on a calc, it doesn't seem to do any harm. Like if you wanted 40 integers and they're going to be 4 bytes, then what you should say is 40 and then 4. But if you accidentally say 4 and then 40, it actually works fine. I think internally it may just plain multiply them together and then set the whole memory area to 0. All right. Realloc is actually kind of more useful in some ways. Realloc, if you have a memory area, you give it the pointer to your memory area and then the size you would like it to be next. And usually this happens because you allocated memory and then it's too small. Like you were holding a list and it grew and grew and grew. And it will try to resize in place. So if there's nothing after it in the heap, it allows the operating system for that memory and then just say, oh, hey, now you've got more memory. But it will also move the data if it has to. So it may be faster, it may be slow, it's hard to know. Realloc array is similar, but it has the same parameters as calloc right down here. All right, so I think, oh, and it even mentions down here with realloc, it is equivalent to the call right there, just multiplying the two things together. Okay. So I guess that's about it on that. Oh, we won't go there right now. All right. So in user space, you might be tempted to use stuff like a C++ vector if you want something that's an extensible data structure. In the kernel, there are kernel linked lists you can use. Or if you wanted something, so C++ vector doesn't actually use a linked list under the hood. It uses an array, just a regular array. And so it essentially, if it grows too big, it calls realloc and then moves everything over. So kernel linked list, being a different data structure, gives you different performance, for example, seeking to some spot in it or whatnot. But it's a readily available extensible structure. If you want to use something a little bit more exactly like a C++ vector, what you just have to do is, if you run out of space, go ahead and reallocate it and move if you need to. Then you have something similar. There's no such thing as a template class in C, and so an awful lot of the things that the C++ vector does just simply don't really exist here. For example, a C++ vector can be used to call destructors automatically. We don't have destructors. All right. Let's talk about goto a little bit, and goto being used in the kernel. All right. So I'm going to go to source on here. Source. All right. Grep r goto everywhere in here. All right. So here are lines that say goto somewhere in them. How many were there? 155,746. So you can see goto is referenced pretty often in the kernel. If you scroll up through here, you know, this is pretty clearly all cases of goto too. I don't see a lot of other stuff mixed in here. There's one that's not a goto. That's not a goto. It just mentions that the assembly goto in GCC doesn't allow outputs. So not every single mention of goto here. Oh, here, all tests equals unreachable chain test. All right, there's a goto that's not actually a goto, and there's one that's in the name of a function or something. All right, so there's a few in here that are actual gotos, so that number is a little bit of an overstatement. But I think it conveys the main point here. There's a lot of use of goto in the kernel. All right, what is this for? Here, let's go to this file. What are they doing here? All right. That's a typical pattern. Okay, it's kind of a long function, but that's fine. All right, so what's this do? Allocate some memory and give it an address in the guest physical address space. I don't know what they're doing here. But it looks like they're gonna be allocating space here, and like there might be some reasons that it can fail. All right, so down here we say something like R equals check memory region flags. I'm guessing just from the name that this does some kind of check and that it might fail. It looks like if it fails, we want to go to out. Where's out? Out is way down here. All right, there's three outs. There's out slots, there's out free, and there's out. So that one just goes plain to the out. This seems to be the last one that gets out of here without freeing anything. All right, now you can see this one down near the end here. If this thing here fails, we're going to go to out slots up there, which means we'll call it KV free, and we'll call it KVM free mem slot. I'm guessing that those have to do with free memory, again by the names. And so it looks like we might have to do them in certain circumstances. So if you look down here, starting at the top, we have go to out there. Then we have some things they call general sanity checks, and if these fail, we go to out. And then whatever checks we're doing here, it looks like we have to go to out. I'm guessing this here means if we've got too many pages, again, go to out. All right, if we keep scrolling down here, eventually we do this KVM arch create mem slot, and so it looks like at this point we've got something that we have to free if things fail. And so we start going to out free instead of just plain out. All right, where's it actually allocated? I don't know, it kind of looks like maybe there. All right, then after a while, we go to out slots instead. And so I'm guessing something in here, like maybe this or something like that, sets up memory slots that have to be disposed of in some way if things fail. So we have out slots. All right. So these out levels are kind of in inverse order of how much we have to do to get out. When we're further into the procedure, it looks like there's more stuff that has to be undone, and so we have kind of higher levels here in terms of what we undo. There's the return on the function right here, which is kind of like, well, we made it to the end of the function and everything's fine, so we turn 0 to indicate everything's fine. Otherwise, we return R, which I assume is holding some kind of error code at that point. All right, so that's a really typical use of goto inside the kernel. You see that kind of use all over the place. If I go past that and look for something else, so here's a short function. Starts right up here, ends right down here, and you can see if BMA, assuming it's like a BMA fails to work or something, we go to out, and this is our way out of the function. Apparently we have to do that before we leave the function. I don't know why. All right, so that was just in the KVM stuff there. If I just hold the up arrow for kind of a random number of minutes, I will go past, hey, sound stuff. All right, so it looks like some kind of sound driver here. It says Intel and Skylake and whatnot. That's Intel architecture. And all right, so we're inside a device driver here, basically one of the sound drivers. All right, and so we've got a couple of cases here where we might go to load library failed. Right there. All right, where's load library failed? Right down here. Well, apparently if it failed, we have to release it. So that's our way out, like our undo, give up. All right, here it looks like that this base FW load failed. There's a few of those. We can go down here, and it looks like there's a few things we have to do to clean up if that particular thing happened. All right, here's a case I want to show you too right here. All right, keep in mind I haven't been in this file before. These patterns are so common that I scrolled down and I was like, oh hey, that case, I got to talk about it. This function here, bxt load base firmware, guessing it loads some base firmware. It looks like it can fail right down here. We got this dev error, so it looks like things are probably not going very well here. We're down this code path, and we can return this ret here, ret value, which looks like the thing that came back from request firmware, and it was less than 0, so I'm guessing that negative numbers here are error codes or something like that, and we're going to return one. All right, so it must be that there's no cleanup required in this case. However, if we made it down this far, we have SST load base firmware failed, which presumably is down here, and we got to release firmware. Well, my guess is that this right up here, this request firmware is where we originally loaded the firmware. So probably if this thing succeeds, which it did if we're down here, we've got some firmware that we have to unload if something else fails later. There we go. Looks like that's there's a couple of ways that we get to this load-based firmware failed. All right, so that's probably the most common pattern that you'll see on GoTo in the kernel, and I mean you kind of have to get used to it. One of the pioneers of computer science, Edgar Dijkstra, wrote a statement called wrote a paper called "GoTo Statement Considered Harmful," because he felt the GoTo statement leads to spaghetti code, where it's very difficult to understand the code because you've got GoTos going this way and that inside the code. And so his argument was you should use the built-in control structures instead, like for loops and while loops and if statements and functions and that kind of thing. These things can all be replicated with GoTos. You can use a GoTo instead of a loop if you want to. You just, you have your code for the loop, and at the end, if, whatever it is, that means we're going around again, go to the top of the loop. So you can totally write a loop with a GoTo if you want to. And his argument was against that kind of stuff. And in the kernel, that principle is actually mostly followed. Like usually what you see GoTo used for is the stuff I just showed you. Somebody else, whose name I can't remember, apparently not quite as famous in computer science, later wrote a paper called "GoTo Statement Considered Harmful." And in this case, he was saying that Edgar Dijkstra's paper was harmful because the GoTo statement is very useful for cases like this. It's the clearest way to specify, say, output procedures for a function when things have failed. And so, oddly enough, the kernel authors kind of follow both papers. They avoid using GoTo for stuff like loops or if statements or, instead of functions or any of this stuff that Edgar Dijkstra was talking about. And at the same time, they go ahead and use it for things where they think it makes the code clearer. All right. Yeah. So, not necessarily giving a argument that everybody ought to start using GoTo more for stuff like errors. You have to work with the code, and that's what they decided. So, there you go. All right. Now, exception handling in languages that support it, like C++, provides another way to get out of functions in some kind of finer-grained manner, like this. Because you could throw a variety of different exceptions depending on what failed. I'd come up with something like that. But anyway, that's not the way the kernel goes. Okay, so that's that one. Oh yeah, pointers to functions. We got to talk about pointers to functions. All right, so we did.
And we could skip that part and the next part.
Well, we'll cause a little trouble later. All right, so we use these with things like p-threads, and I don't remember if we had a lab with p-threads or not in cs-253. If we didn't, we probably should. Maybe I should make up one if we don't. I'm teaching it again in the spring. All right, now we'll do things that are more silly. All right, so this word scrambling functions one, I think I've got that sitting around still. All right. No, that here, we're an example of this area. All right. So, yes, scrambling. All right. I spent a while writing this last time, so I think I'll show it to you and it'll speed things up. But let me give you a real simple example first before we get into this. All right. So languages are often described as having or not having or partially having first-class functions. A first-class function means that you can treat a function as a value. So you can do anything with the function that you do with a normal value. So if you can do it with an integer, you can do it with the function. All right. So that includes stuff like passing one to a function and things like that, and of course storing it in a variable. All right. Let's look at the math library real quick. Okay. So math has trig functions in it, like sine and cosine and things. And so for example, with sine, this is the pattern we follow. It returns a double, it takes a double. So if we wanted to make a pointer to it, we could say something like this. double, that's the return type. I'll call it trig function, and then the parameter it takes is a double. And so I'll go ahead and include math up here. We can put sign on there. So now we've got a pointer to it. All right, this is done in radians. So if we say like the sine of 3.14, let's go ahead and turn up it. We'll see it. Okay, it's on LF. All right, so that should actually run the sine function. All right, one note about building this thing. Since we used stuff from the math library, because when we compile it just like this, we actually get an undefined reference to sine. The math library, though it might seem, is not linked into programs by default with GCC. You have to pass it a special flag, that's LN, and that links to the math. All right. There we go. There's the sine of pi. I think that's what it should be like. It's 0 if you get the sine of actual pi, but I just said 3.14. All right. I'd be a little closer if I said something like 3.141592653. There we go. 0.00000. Sure. Okay. But you know, whatever. No, it doesn't match my comment. All right. So what if we say trig function equals cosine? There we go. We'll change it. I'll change my comment there. Of course, I don't have to. I'll call it TF for trig function. There. Now these lines are identical, exactly the same. But they're going to have different results because trig function is pointing somewhere different. All right. So that's a function being stored in a variable. That was one of the things we were talking about with first-class functions. All right. Maybe I'll make a function that returns a function. This is complicated in a syntax sense. All right, so what I want to do, leave that alone for a minute. I'll call this return tangent, and it doesn't take any parameters. And what it's going to do is return tan from the math library. All right, I said this is a little complicated. Okay, so the type that we're going to return here can be described like this. Double, all right. If we don't have a name, then I guess we just have a star, double. And so that's what we want to return. And I want to call the function return tangent. Let's see what happens. Yeah, not okay. All right. I think if I remember right, it goes like kind of in the middle of this. Like that. She'll look this up beforehand. All right, it appears to have compiled. Let's see if it works. Return tangent. Will it return the right value? We'll see. All right. I think that's the tangent of it. What's the tangent of pi? You're nodding like that's the right one.
Well, it's
Right.
like that over -1, right?
Yeah, yeah, that should be right then. All right, and we're gonna check to make sure that the return is working right. So we change this to something else like return cosine for a minute, which I realize doesn't agree with my descriptions. You can see now it changes to the cosine of it. All right, so there's a function that returns a function. You can see the syntax got a little convoluted, but we can do that. All right, can we pass, what's that?
That was right, negative 0.00159.
Okay, cool. All right, can we pass a function to a function? Yeah. All right, let's make one, it's not going to return anything. And this is going to print out like a function, a trig function run on a few different values. All right, so they run on angles. And so here we're going to take a function, it's going to return a double, and it's going to be a pointer, we'll call it TF, and it's going to take a double. All right, So that describes the parameter there. And then I'm going to go ahead and make a list of values. All right, and I'm going to say, this is getting cumbersome with the whole pi thing. All right, now pi is defined. All right, so 0, pi divided by 2, pi, pi, the next one, like 1.5 pi. I guess we could do that. That's usually not how they state it in trig, though. They usually say it times 2 divided by 3 or something, don't they? No, they don't. That'd be weird.
That'd be 2/3 pi.
2/3 pi? Yeah, that would be 2/3 pi. All right. Luckily, Alan Payne hasn't walked by and laughed at me yet. All right. So, there we go. We got like pi, a 0 and a half of pi, and an all of pi, and then 1.5 of pi, and then 2 of pi. Okay, that goes that. All right, that would be 5 in total. I don't do that. Okay, so we'll say TF percent sign LF equals percent sign LF. All right. And that would be values I and TF of values I. All right. Why do I have a problem there? I have a parsing problem. Oh, there it is. There we go. Better. All right. So void so doesn't return anything. All right. So instead of all this stuff, we could say something like run on angles of say sine. All right. So what did we do there? Oh, I didn't say this isn't right. Isn't right. Oh, and this is the curly braces. I wrote that like Python. Oops. A lot of times when I deal with first class functions, it is in Python.
Nice.
All right. So there we go. There's values around the circle of sine, kind of with coarse gradations. All right. So yeah, we can do that too. That's another first class function thing. The only first class function thing that C does not deal with very well is if you are creating a function inside a function and then you're going to return the one you created, but you're going to return to a variable that was local to the function that is already ended. You're kind of like, why would I ever want to do that? That's a valid point. Sometimes I show an example where you have a function that returns a counter and you run it again and again and again and it keeps counting. And I can make it work in a lot of languages, but not necessarily C. Only when I have two counters that return from the function. It's a little hard to find a spot where C's first class function support is really inadequate. This is how it works. All right, the main problem thing where I struggle with C's first class function support, notice with this one up here, I was like, how's this thing go again? I should look this up before I came and taught it. Ultimately, I did remember it, but it's a little bit complicated. Yeah.
So if you wanted to define a function inside of a function, could you like give it like allocate it to the heap or whatever, and then return like the heap address of it? Or?
Yes, yes you could. Yes, that would work. Yeah, and you can definitely define one of these in here. I'm going to go ahead and keep my syntax there. All right, so I'll just make another function, and this will just be like some made-up function. Okay, for double, and it takes a double, and it doubles it. No, 2 times x, doubles it. All right, there we go. Since return double doesn't really use anything in particular on the heap or whatever, we'll be fine. Okay. Okay. Let's call it make something. All right. So if I want to go down here, I can say something like run on angles, make something, but we're going to call make something. So the make something will go ahead and return this function is defined right there. So this function returns that function, which gets passed to this function, which runs on each of these values. Is that going to work? I feel like I just set up some kind of crazy marble
A lot
trap
of experiment,
or something.
yeah.
Illegal instruction?
Hmm.
I think my marble just went off the track. Make sure this actually works. We'll take this a little bit simpler. Is that part okay? That part's okay. What if we try and run it? Okay. That part's okay. What if we try and pass it to run on angles? Illegal instruction. I'm not quite sure why my marble's off the track actually. Because looking at this, it seems like it works fine here. And then when I pass it in there, somehow.
Don't you need the parentheses and some kind of value after trig function there?
Right here?
Yeah.
No, see how well, I'm gonna call it right here. But I'm not trying to call it right here, I'm trying to pass it through.
Oh.
I wonder if I need to dereference at one level. No, that's not it. Alright. Well, I'll have to think about that one later. I'm not sure why it's doing that. But certainly we did manage to actually return a function from right here, and that was fine. I'm curious now, if I say run on angles, return tangent. Oh, I think I might know what's going on here. Alright, so let me see if I can, I don't want to necessarily fix it. Alright, I think what's happening here, you see make something here, I define a function inside of make something, right? Make something's stack frame, however, has been discarded when make something is done. So I think what's happening is down here, when we run make something, we're putting something in here that's actually reference to something that was inside of make something's stack frame. Then right here, we're still fine because although the stack frame isn't being used anymore, it hasn't been deallocated yet. So we're running it there. On the other hand, when we call another function, it overwrites the stack frame. Here's a way to try to confirm this hypothesis. So suppose I go ahead and do this twice. Printf will also make a stack frame. And yeah, the magic only works once. Although I shouldn't quite say that. The function that makes something returns is somewhat ephemeral here, and it works until we call a different function and overwrite the stack frame. All right. Okay.
But if you gave it its own permanent piece of memory, then it might work, right?
Like if you malloc trig function and then assigned it to make something, it might stick around for the.
It's possible. You might run into a security measure. Because you'd be trying to execute code on the heap. Executing code on the heap is kind of a hacker trick. But unless it triggers a security measure, that could potentially work. Yeah. All right. Well, anyway, there's we got partway there. All right. Well, anyway, I was talking about a different memory error that you've actually run into trying to do this sort of business, and I found you another memory error that you run into if you try to do this, go this far into the
Wait,
nonsense.
there's more than one?
All right, eventually you'll get to a problem. Python, on the other hand, will be happy to run with you through this scenario right here. Okay, and a lot of other languages, and including C++, actually, with the Lambda system that they've added in C++ about 2011, I think, or 14. All right, so there's a way. All right, so we could also store these in pointers or arrays or whatever. So one more option I could have done here is I could have put the trig functions into an array. I could have said something like double, all right, a trig function, double, but we're going to actually in this case have an array of them, and it's going to equal sine, cosine, and tangent. All right. Just get the three main ones. Then we could say something like 4 and I equals 0, not less than 3 in this case, I plus plus. We're going to run on angles on trig function. I'm going to call this trig functions, pluralize it. All right. There we go. So we're getting kind of a lot of output here. Where did that start? I don't remember quite exactly that. Remember, tangent is the one where it kind of goes off with a tangent line along the axis heading towards infinity. Anyway, that's why we've got some pretty astronomical values for a couple of these. How the trig function works. All right. Review of trig at the same time as computer science. Fun, right? Especially if you're in the same class, if you're in trig this semester. All right, so there's an example of putting the functions into an array. Okay, the main thing I find difficult to deal with on C is this kind of weird inside-out syntax where this is the name of a variable and there's where the braces are. Because in C, a lot of times we get used to this in C. All right, we'll have like type and variable name. And then we might have equals some value. Like, that's our standard way we put this together. But function types don't follow this model. Indeed, they do not. Turn type of function followed by a star, then the name of the variable, parameters for the function equals, the value. All right. So you just have to get used to your function types are a little bit more complicated. The name of your variable is actually in the middle of it, and once you've been looking at them a while, they get a little easier. I mostly pause a moment when I'm doing stuff like this, because if this makes something function, say if instead of returning double, it like has some multiple on here, I could say something like double multiple. And we return multiple times x inside our function here. This is the parameters for the function make something, and this is the parameters for the function that makes something returns. Now this is not a common construction in the kernel at all. You probably won't see these ones much. This kind of thing, on the other hand, is pretty common in the kernel, especially inside structures. And so we were talking about that earlier. If I go to either SSD, Linux, source, 4.19, whatever, and we were looking at FS and export operations. If I go to something I've never looked at before, let's go over to nilfs. I believe nilfs is a file system that does mostly not file system things. I forget why. It occurs to me that it might have to do with SSDs, but I don't know. I'll look it up someday. All right, but a really common model for these file system functions is where you export these operations. So if we look at name i.c, and we got not just the export operations. I was hoping they did structure it that way. A lot of the file modules are. Not just export operations, but we've also got inode operations. And actually there's another inode operations there. And then there's another inode operations up here. An inode refers to a file. And I'm not quite sure why in nilfs is exporting 3 different types. It looks like they have to do with whether you're using a directory or a special one or a symbolic link. Presumably somewhere there's ones for a normal file. So you can see we've got different operations that we can do on inodes. Like we can create them or look them up or link them. And then for these export operations, we can do stuff like get the parent for it. But anyway, each of these have some function inside the underlying file system. So the way the kernel uses these, suppose you were to go onto the system somewhere and say, I've got some files, cat hi.c. All right, so the question here, I suppose, is what function does the kernel run in order to read from this file hi.c? And so if I say mount here, there's a few things mounted. Let's grep for, say, probably on slash actually, which is a really terrible thing to grep for. Alright, anyway, so slash is mounted right here using ext4. So if we're going to do a read in ext4, it's not in here, ext4, alright. So there's a bunch of things that are like bred or read or whatever. Looks like name i.c is some of this. Alright, doesn't have an operation for read exported. Okay. There's a couple different permutations of read that are used in different circumstances. Alright, but it looks like at the end of all of this, it would have been super handy if it had like a read defined in this file. Alright, I'd have to look around a little bit. This file that I've looked at is going to have some of these operations with it. And maybe it's in a different file where they put together this structure that has read inside it. It's probably in export operations. Alright. We'll actually find it. Maybe not. Alright, somewhere buried in this 100,000 lines of code that defines ext4, there's going to be a function somewhere. It's going to be put in some kind of structure, that I can't find today. And it's going to get called when I try and cat a file in here. On the other hand, if I go to say slash, say, not TP, I want proc, and I cat CPU info, this is going to be running a completely different read function that actually queries information about the CPU and then returns it like I just read a file, even though there actually isn't any file. It's just a directory entry that calls a read function and there it runs. We'll make that kind of thing in slash proc fairly soon, and so we'll be exporting our own little operations. There's a proc file operations kind of structure that we'll use for that. I look at kmod and this is a little example I wrote that exports a file operations. If I look for file operations in ext4, I might actually find it. We have file operations that are defined here for our file, and essentially they are functions. So if we were writing an actual file system, these functions would take care of finding the file and extracting the contents from the hard drive and returning them. And actually, I'm going to pop back over here for a minute. It looks like, I can do this. Look at that. I'm typing so slow, you can read. Alright. Looks like dir.c. Hey, there's read. It looks like it calls generic read dir. I don't know where they defined that file. But it does look to me like, well, it's because this is ext dir operations. It may be when I read a directory from ext4. Anyway, we probably run that function today. Alright. Looks like there's an inode one in there. And there's actually this, in ext4, we got this ext4 file operations right there. And it looks like in file.c, this one's defined. And has the iterative approach on the read. You can define either a read or a read iter, and they work a little bit differently. This is probably the name of the file that we ran, or the function that we ran when we printed out that file. And so if I say ext4 file read iter. Alright, it looks like it has some various unlikely error conditions, and it might be configured so you do that. And if not, you run generic file read iter. Or is that defined? Oh, I don't know, not that file. Yeah.
Is unlikely in that context? Is that like a keyword or just like a function?
That's a compiler directive that informs the compiler. So the compiler is setting up a branch condition. Without knowing in advance, the compiler will assign an equal probability to each way. And so it could be, for example, that you have a jump, and so when you reach that condition, does some kind of conditional, need to jump somewhere else, or it just keeps on trucking. And it just keep on trucking may actually run faster on that architecture. So if it's unlikely to go some branch, you want to set that one up as the jump and then just keep on trucking as the main one.
Okay.
There's a number of optimization keywords you can give GCC to do stuff like that. For example, if you declare a function to be inline, it will try to kind of put it in by cut and paste instead of doing an actual function call, which is often faster. Now, mostly with these hints, like the inlining functions, I almost never use the inline keyword, and the reason is I'll usually just let the optimizer decide. It can look at how long the function is and decide if that ought to be inlined or not inlined, depending on how often I've used it and stuff like that. But they put in unlikely because there is no way the compiler optimizer could have any idea which branch is more likely there. So mostly just tell the compiler stuff it can't figure out anyway. Yeah. You can use register on an int. You can say like register int such and such. It'll do its best to keep the int in a register. But you know, again, if it should be in a register, hopefully the optimizer figures that out.